Okay, very good morning. So, let us get going on Bayesian estimation. I explained to you yesterday the essential principle of Bayesian estimation. You start with a prior uncertainty on the parameter, and again to remind you, in the Bayesian framework we assume that the truth is not fixed as in the classical methods, but then of course the truth is assumed to be random, but the way to perceive it is that it is not the truth per se that is random, it is our knowledge of the truth that is kind of uncertain, and we essentially we are looking at the truth plus our uncertainty together, and the hope is that the data will refine that uncertainty and get us a more precise estimate. So, therefore, we have a concept of prior and posterior, and the main or the central task in Bayesian estimation is in the computation of this posterior given this prior, and of course, the likelihood you can say, or the conditional observations of the measurements or parameterized PDF, conditional PDF of the observations given the parameters, which you have to assume. So, the user has to supply both f of theta and f of y n given theta, and c is a constant stemming from the fact that we had this f of y n here, and we said this f of y n is independent of theta. Nevertheless, it is a constant that has to be estimated. You cannot ignore it, but the nice thing is you do not have to evaluate f of y n, you treat it as a constant and evaluate the constant in such a way that this left hand side is a legitimate PDF. What we mean by legitimate PDF is the area under it should be 1. So, that is how you estimate the constant, that is it. So, beyond this, as I said, it is the user's call as to what the user would like to do with this posterior, but the main point again, apart from the fact that there is a stark difference between the philosophies of the classical methods and the Bayesian methods, the second significant difference is we obtain interval estimates, we do not obtain point estimate. However, we can derive point estimate out of this distribution of theta in a few different ways. I will go through that. For example, I could say that I would like to pick the average of the estimates that I have obtained. F of theta given y is the PDF of conditional PDF of theta given y after the experiment has been performed. I can ask for the average, which turns out to be the conditional expectation. So, the first point estimate that I can construct is the mean, in fact the conditional mean specifically of theta, in other words expectation of theta given y, which is nothing but the average of f of theta given y. Now that we have decided to work with some number, an average of the interval of estimates that we have obtained, we can turn to other averages as well. What we mean by other averages is we can look at median of that is conditional median again, or we can look at mode, once again conditional. So, we can look at any of this, we can work with any of these estimates and derive a point estimate, which is completely the flipped way of what we have been doing in the classical methods. So, the whatever point estimate that you pick, fortunately now you can show that picking any of these point estimates amounts to solving an optimization problem. So, here we are not solving any optimization problem, you must have observed by now. We are not maximizing likelihood, we are not minimizing approximation errors, nothing. We are just saying I will compute the posterior, and from the posterior I am going to derive this point, one of these point estimates. And the nice result is, regardless of which of these point estimates you work with, you would essentially be solving an optimization problem at behind the scenes, where you would be minimizing what is known as a risk function or a cost function. So, let us quickly go through these 3 estimates, different point estimates, and ask what is the equivalent optimization problem I would be solving? I would still not be solving that optimization problem, but it is heartening to know that these estimates, respective estimates are optimal in some sense. So, the first in order is this conditional expectation, which is known as the Bayesian estimate. Although the general Bayesian estimation, when we talk about it, it always refers to computation of the posterior. Specifically, when you say I am working with a Bayesian estimate, you are working with this conditional expectation, which also happens to be the minimum square mean square error estimate. That is, this minimizes the sum squared error between the estimate and the truth. If your estimate is theta hat, then you would be essentially, this is a solution, minimizing, find theta hat such that this is minimized, and that is a conditional expectation, we know that already, right. And that is exactly what your equation is telling you, equation 23 is telling you, the cost function that you are minimizing with a slight change of notation. But you should understand that by working with this conditional expectation, you are essentially solving an optimization problem of this type here, where you are minimizing the mean square error. So, this is very nice because early on in estimation we said I would not know the truth, so therefore, I can never solve this problem, but here is a solution to that problem. Without knowing theta naught, we are actually able to obtain the minimum mean square error estimate, and that is why the Bayesian estimation is or the Bayesian estimate is very good. The celebrated Kalman filter is actually a Bayesian estimator. You can show that it is a minimum mean square error estimator. And of course, we have already known, we already know what is this, why is this result optimal, as we have been saying the conditional expectation is the minimum mean square error estimator. And how would you compute this from the posterior using this expression? Of course, in practice, you may not have an analytical expression for f, or you may have, that depends on the situation. It completely depends on the situation. In early days of Bayesian estimation, maybe over the last 2 decades or so, the prior and posterior, sorry, the prior and the likelihood were chosen in such a way that you would get an analytical expression for the posterior. So, let me give you an example. Suppose I assume that the measurements have Gaussian distributed errors conditioned on for a fixed value of theta. F of y given theta is Gaussian, like we went through the example yesterday. Then what prior should I choose so that I can obtain a closed form expression for the posterior? The likelihood will have a closed form expression. I can write an analytical expression for the joint Gaussian PDF. But there is no guarantee that when I multiply 2 PDFs, I can show that the resulting PDF has some closed form expression. Simply because I multiply 2 PDFs, it does not mean that I will always be able to express the resulting product in the form of a known PDF. When the priors were chosen such that the posterior PDF could be expressed in a known PDF form, those priors are called conjugate priors. So, that was the basis for choosing the prior. It seems a bit strange because we said prior is supposed to represent my knowledge, prior knowledge of theta, and now you are saying prior is driven by computational considerations. Yes, that is true. When you are falling short of computational power, you will have to make some compromises, and that compromise was made here. Then the question that arises in mind is, what if the prior that is governed by computational convenience is not the same as the prior that I would like, that I have about theta? What if they two are different? Will the estimate go berserk? Will the estimate be in error? No. Actually, in general, in Bayesian estimation, even if you were to choose a prior that is different from the so called true prior, you would still end up obtaining decent estimates, but the number of observations that you have to collect to obtain a certain precision is going to change. What is the premise behind Bayesian estimation? You start with some uncertainty before the experiment, perform the experiment, analyze your data so that you obtain a more precise estimate, that is lesser uncertainty. Suppose I were to fix the uncertainty, I were to say that I would like to have an estimate with a certain precision, and I start with prior 1 which is a truth and prior 2 which is different from the true prior. Then would it make a difference to the precision that I want? No, I can still achieve the precision that I want, but where it makes the difference is the number of observations that would be required to achieve the desired precision. When I show the example, part of this can be understood, the other part maybe you have to simulate and figure out, but that is the point, because this is a question that is often asked when by beginners in Bayesian estimation. What if I choose a wrong prior? There is nothing like a wrong prior. I mean, it will take more observations to achieve a certain precision. So, to go back to the choice of prior, essentially you would choose the prior in early days, even to a certain extent today, such that the product of this prior and the likelihood can be expressed in a closed form, in some known form of PDF. Today you do not have that restriction because of the computational power. Essentially what you now have is very high simulation power. So, over the last few years, I would say probably less than a decade, we have now what are known as Markov chain Monte Carlo simulators, MMSE simulations, which allow us to work with PDFs that do not have a closed form expression. After all, why do I need to know the posterior? I would like to be able to compute this conditional expectation or the median or the mode. I should have the PDF either in a mathematical form or some values. So, what this Markov chain Monte Carlo simulators would do is they would actually run for different realizations of y. They would actually figure out what is the resulting theta, the possibilities for theta, or for a given y you can say for different priors you can figure out what the posterior is. So, it would sample the space, and that sampling the outcome space has to be done in a computationally efficient manner, and that is the key in the Markov chain Monte Carlo simulators. So, in other words, today this PDF, this posterior need not be available in a closed form expression, it can be available in numerical form. It essentially gives you the probabilities on small intervals in the theta space. And using those numerical PDFs, you can compute the conditional expectation. So, you replace the integral with a numerical integration and go ahead and compute. Of course, they are going to be more intensive than your regular MLE or even least squares, but that is okay. Today we can afford large computational powers, and you must have observed in many mathematical fields today, people are now slowly resorting to proving certain theorems by way of enumerating all possibilities. So, it is like a brute force method which was considered bad earlier, now is being considered good. It was the brute force method, that is doing an exhaustive search for all possibilities if I am proving some theorem, was considered bad. The pen and paper version was considered elegant. It is still elegant, but it was considered bad because primarily because we did not have computational power to do an exhaustive search. So, there was a recent Fermat's conjecture, I do not know if you must have heard, that was actually it was not possible to prove, at least until such a time, analytically or mathematically, whether that conjecture is correct or not. Whereas they did an exhaustive search, but using clever computational clever search methods, and showed that that conjecture is wrong. Okay. But it required quite a bit of intelligence to do that exhaustive search. One small inefficiency in that search would really blow up the time taken to figure out whether that conjecture is good or not. So, eventually they proved that conjecture does not hold. So, here in Markov chain Monte Carlo simulation, some intelligent kind of sampling is used, and for those of you who are familiar with Kalman filters, you would have also heard of particle filters and so on. So, these particle filters also rely on this sampling in the outcome space approach, a clever sampling of the outcome space. So, to come back to the discussion, to compute this conditional expectation, either you need f in analytical form, closed form, and still maybe you will not be able to evaluate this integral, you would perform a numerical integration. But today you have the luxury of working out this integral again in numerical form, even though you may not have f in an analytical form. Okay. The second estimate has got to do with the mode, although I have written here median in the order. The second popular estimate, the first one is called a Bayesian estimate, which is a conditional expectation. The second one is called a MAP. MAP stands for maximum a posteriori estimate. Okay. What we are saying is, if you know from the theory of from the probability theory, mode is nothing but the maximum of the PDF. So, in this case it is a maximum of the posterior. Okay. We know that mode is essentially the value of the random variable at which the PDF peaks, and that is why it is called a maximum a posteriori estimate. And you can show that once again this map minimizes some kind of a cost function, and that cost function is given here. Thus, that cost function is again in terms of the error between theta and theta naught. So, if you look at the cost function, it is a kind of a discontinuous kind of cost function. It basically sorry, it is minimizing this cost function, and it is called a hit or miss estimate. That means either you are in the correct region or you are not with this kind of an estimate. But the beauty with this map is its very close similarities to MLE. So, let me go back to this expression, the original expressions where you have posterior as the function of likelihood times a prior. If you look at this expression carefully and I write this in logarithmic form like we have done there. So, log of posterior is logarithm of likelihood plus logarithm of prior, right. So, if you look at this carefully, the first point to observe is, suppose I assume f of theta to be constant. When is the PDF constant? For what kind of distributions is the PDF constant? Uniform, which means I am saying any value of theta is likely. I have no specific knowledge of which are the more likely values and less likely values. I do not know. The average temperature, anything between 0 Kelvin and maybe 6000 Kelvin or whatever is the temperature of the sun, that is possible for this average room temperature. It is ridiculous, but you can in principle say that and still get away with it. So, let us say we say that any value is likely, equally likely. Then basically this boils down to a constant. Yeah, there is a constant here. So, let me write that constant as well. So, this is absorbed into this constant. So, what you are left with is simply the posterior being the likelihood, scaled likelihood. And when you are evaluating the mode of this, all you are doing is picking up the MLE. So, the MLE therefore, as much as to Fisher's dislike, is the Bayesian estimate with a uniform prior. That is all. It is a Bayesian estimator with uniform prior. If I assume any value is equally likely and perform a Bayesian estimate, I carry out this and pick the map. So, that is very important. So, the complete statement is MLE is the map estimate with a uniform prior, not simply Bayesian estimation. Bayesian estimation would mean conditional expectation. It is a maximum a posteriori estimate with a uniform prior. Now, we know we have a different perspective of MLE. We have been thinking all along, we have been viewing MLE all along as an estimate that maximizes the likelihood. But now we can take a different stance and we can say, well, no, it is actually an estimate that is the maximum of the posterior after I have conducted the experiment. Among all possibilities, I have picked up the maximum that maximizes the f of theta given y if I begin with a uniform prior. This is the perspective that Fisher obviously vehemently argued against, because the framework in which MLE is set up is theta is deterministic. The truth theta naught is deterministic, whereas in the Bayesian framework the truth is random. So, he says the philosophies themselves are different. How can you by sheer mathematical equivalence absorb my approach into the Bayesian? So, as I said, okay, fine, people said that is fine. How long will you stay to argue? Okay. With all due respect to Fisher, they said, okay, fine, no problem. A few papers from you, that is it, right? We will wait for some time and then start teaching that MLE is a special case of Bayesian. So, I hope wherever Fisher is looking at from the skies is not upset with me, and I keep saying this, but anyway, you should still nevertheless keep that subtle but very important difference in mind while mathematically accepting the equivalence, all right.